For the construction of planetary rovers, the area of visual processing is of major importance. This is because, unlike most robots on Earth, robots on other planets or satellites can barely be controlled remotely. This is, for example, due to the signal delay and the limited speed of light. So there needs to be some autonomy. This means especially that the robot needs to navigate its surroundings successfully. And for this, it is necessary that it can process its visual data successfully. In the following video, some quite common methods of visual processing will be presented. It is mostly based on the book Planetary Rovers, Robotic Exploration of the Solar System by Alex Ellery. A planetary rover is mostly presented with a 2D image of its surroundings. And these surroundings need to be reconstructed using this image. Without any further constraints, this is a version of the inverse optics problem that is heavily under constraint and not solvable. And this is why some special assumptions need to be made. From those assumptions, information about the surroundings can be derived. To see how this is done, one can first consider how the human brain does exactly the same process. One approach is to say, okay, the human brain, when presented with some image, as for example this image of Mars, the human brain firstly segments this image into uniform objects or uniformly consistent areas. Afterwards, those areas or those objects are characterized and some properties are derived. The properties that can be used to segment an image into uniform areas can be color, light level, or texture. Also, those unitary areas are often naturally segmented by edges. The characterization of those areas can be done by special invariant features, as well texture, color, and shape. For example, an area of a certain texture might be some special rock or might be some type of sand. This video will firstly focus on the detection of edges that can be used for the segmentation of images. After that, it will consider methods of the characterization of areas with its main focus on texture characterization. As most planetary surfaces deviate mainly in light intensity but not in color type, almost no information is lost when considering grayscale images. For further computation, those grayscale images can be easily described by matrices whose every component corresponds to the brightness value of a certain pixel, as visualized by this image. Naturally, finding edges in images is quite a difficult problem. This is already apparent in phrasing the question for the definition of an edge. When presented with two areas of different light value, is the edge the line of transition from dark to bright or from bright to dark? In other words, does it belong to the left side or the right side of this picture? Further, how thick is an edge supposed to be? One could, for example, consider a broad line to be an edge, even though it has a width of more than 1 pixel. In this video, an exact definition of an edge will not be provided. Instead, some desired qualities of a good edge detector will be presented. Firstly, a good edge detector must avoid false negatives and false positives. Additionally, the detector's edges must be as close to the true edges as possible. And finally, the edge detector should return 1 point only for each edge point. When presented with an edge that is a transition between two areas, this edge should thus be as slim as possible. Further, small deviations of the detector's edges are not of big concern, since they only influence the image segmentation slightly. In this image, the white line might be considered as an edge due to its high lightness intensity value. This image can be transferred to a matrix and then to a discrete function. And this function, again, can be extended to a smooth function. It is apparent that the potential edge is a line of high gradient of the smooth function. And this intuitive observation can be formalized by considering the discrete approximation of the gradient. If a pixel is part of an edge, it has a high intensity difference to its neighbors. Thus, this vector here has a high norm. This basically means the vector whose first component is the difference between one pixel and its left neighbor, or its upper neighbor, depending on the conventions, and the difference of the pixel to its left or also respective upper neighbor. And it is apparent that this vector is in some sense a discrete approximation of the gradient. For further computation, this can be formalized using convolutions. Given two matrices I and J, the convolution J star I is defined as apparent here. And okay, this definition might seem a little difficult, but what it basically means that a convolution replaces every pixel or every component of a matrix with a weighted sum of its surroundings. Further, if a pixel or component of the matrix is too close to the edge, the surrounding pixels that are in some sense not part of the matrix or the image anymore are just set to 0. With this convention, this matrix here basically contains the first components of every discrete gradient of every pixel of an image. And similarly, this matrix contains the second component of Z gradients. Already mentioned, this of course discounts for border pixels of the matrix or image. However, as we are looking for image segmentation methods, border pixels are not of the greatest concern. Further, this method that has been introduced here has some major disadvantage. This disadvantage is that it only considers the difference in two specific directions. This means that every pixel is only compared to its left and its upper neighbor. However, this problem can be approached by using different convolution matrices. Instead of those matrices can be considered. And what they basically do is that they compare pixels in every direction. And after applying those two convolution masks, or respectively those two convolution masks, for every pixel, the norm of this provided discrete gradient can be computed. Finally, the provided value of this norm, or of all those norms for every component of the matrix, finally, this provided value is compared to a threshold. When above this threshold, or when the value is above the threshold, a pixel can be considered as part of an edge. This process is visualized by the application of the Sobel edge detector on this image of a pair of glasses. The first image just shows the grayscale image of the pair of glasses. The second image shows the first two steps of the Sobel edge detector, which are the application of the two convolution masks, and afterwards the computation of the norm. And the third image just shows the result of the thresholding process. In this context, a pixel is white if and only if it is considered as part of an edge. Of course, further convolutional edge detectors exist. For example, discrete approximations of the second derivative or the Laplacian can be considered. Zero crossings of this operator also correspond to edges. These previous methods provide good edge detection for uniform areas where light settings are somehow constant. However, most real images contain noise and textures, and those two effects also cause points of high discrete gradient, even if there is no edge. There are several methods to approach this issue. When presented with noise, hysteresis thresholding can be applied. This kind of thresholding makes use of two different thresholds. Firstly, for every pixel, the result of some convolutional masks, the calculation of a norm or something like this, is the result of those calculations is compared to a first threshold. If that value is above the first threshold, the pixel is considered as part of an edge. Further, if another pixel, or for another pixel, the resulting value is above a lower threshold number 2, and this pixel is connected to some edge, this pixel is also considered as part of an edge. In the previously presented image of glasses, this would provide a better edge detection method, as for example, this line is only partially above the first threshold. Further, dynamic thresholding can be applied if there are areas of different light settings. Dynamic thresholding depends on the pixel position so that proximate point intensities determine the local threshold value that is used for the threshold comparison process. Additionally, there are completely different approaches to deal with noise and texture in the form of smoothing masks. When presented with texturized images, the human brain tends to smooth them. This can be seen very well with this painting by Roy Lichtenstein. Even though the skin is made up by a non-uniform texture, it seems as of one color. Mathematical approaches to this can be done by replacing every pixel with the average of its surrounding area. This can be done, for example, with this convolution. Basically, this convolution replaces a pixel by the standard arithmetic average of the pixel itself and the 8 directly surrounding pixels. However, such an average should focus more on pixels with a higher proximity. This can be done by deriving a convolution mask from the two-dimensional Gaussian function. When weighting points in an average with function values of the Gaussian function, it can be seen that points with higher distance from the center have lower weights. Thus, a convolution mask can be computed by setting the components of the convolution matrix to function values of the two-dimensional Gaussian function and then norming those values by dividing through the sum of all components of that convolution matrix. These introduced methods already allow for a high number of edge detectors, as the Maher-Hilbert operator, the difference of Gaussians, and many more. They allow for some widespread applications in planetary exploration, apart from image segmentation for rovers. In one paper, for example, the Sobel operator was used to predict the movement of dunes on Mars. However, those classical edge detection methods suffer from different issues, such as false positives and broad detected edges. Using edge thinning techniques, however, another edge detector was introduced in 1986 by Canny. This edge detector begins by applying a Gaussian smoothing mask. After that, one of the previously mentioned discrete gradient convolution masks is applied. Additionally, the directions of the detected edges are derived from those discrete gradient convolution masks. Using this, the edge can be thinned by removing points that are perpendicular to the given edge with non-maximum value. Finally, the previously mentioned hysteresis thresholding is applied. Even though this edge detector is comparably old, it is still de facto standard with excellent performance. Further, it has all of the previously introduced desired properties of edge detectors. This image shows an exemplary application on an image taken by a Martian rover. As announced earlier in this video, the characterization of objects is necessary after their segmentation. This can be done in accordance with color, shape, and certain invariant features. Examples of those invariant features are so-called moments, which can be calculated with formulas like these. The calculated values are independent with respect to certain transformations, such as rotation, translation, and so on, which is a major benefit. Another useful property for characterization is texture. Texture can be classified by using so-called hydraulic parameters with such formulas. Here, delta I encodes the intensity difference between two certain pixels. A further approach to classify texture provides more insight into the nature of texture itself. Texture itself is in some sense a periodic pattern in two dimensions. This can be, for example, seen by looking at my shirt. It has in some sense a texture, and this texture is periodic in two dimensions. Thus, it is in some way similar to sound, because sound is also periodic, but of course only in one dimension. And sound can be classified by Fourier transforms and approximated by finite Fourier sums, as indicated by this picture. This can of course also be done in two dimensions. For this, discrete integral transforms with two-dimensional periodic function can be used, as for example, the functions of which the graph is visible now. However, these transfers are not really sufficient, since texture can be quite a local property. By multiplying such a transform function with a Gaussian envelope as a window function, the transform captures only local properties. A graph of such a function is presented here. Further, for different scales of texture, a scaling factor S, and for different areas for texture, a translation factor U can be introduced. This provides a set of functions for which, in this notation right now, psi is the original windowed function. And to classify texture, of course, also other types of function can be used for integral transforms. For example, functions that are derived from absolute values and norms. To summarize, this video showed different classical approaches to edge detection. Firstly, methods for image segmentation using edge detection were introduced. After that, properties of the segmented areas were derived in order to obtain information about them. The area of computer vision and visual processing for planetary exploration is quite broad. A starting point for further information can be the main reference by Alex Gallery, or as well original papers by authors such as Canny, which can be found in the video description.